great way for identifying organic substances that contain hydrogen is through nuclear magnetic resonance spectroscopy. Let's take a quick look at it, focusing on only the most salient points. Imagine your pure sample is 2-butanone, meaning you have a CH3 there, simply a carbon there, attached to an oxygen, a CH2 there, and a CH3 there. Let me tell you what the NMR spectrum would look like. Well, the intensity, that means the area of each peak, is simply proportional to the number of hydrogens. So this CH3 region here will give rise to something that has an area that is relative to the size of 3. This will be 2, and this will be 3. We'll get 3 peaks. There they are, 1, 2, and 3. Now, the integration is shown here. One of them's a little smaller. See that one? The area of the peak gets integrated mathematically, so this line represents its area. And it's a little smaller, so I'm pretty sure that'll be the CH2 right there. One of these is the CH3 that's on this side. The other one's the CH3 on that side. How do you tell which one's which? Well, look at how they're split up. They call that one a quartet, meaning it's 4 individual sub-peaks, or split into a quartet. This one's not split at all. It's called a singlet. This one's split into a triplet. The splitting is due to the neighboring hydrogens plus 1. That's the slightly complicated part that takes a little getting used to, but not really. I mean, splitting equals neighboring hydrogens plus 1. There's my CH3. How many neighboring hydrogens does it have? None. So we add 1. That means it's a singlet. That CH3 peak is right there. This one gets split into a triplet. Does it make sense for this CH3, which is the only peak region that's left? Yes, it does, because how many neighboring hydrogens does it have? 2. Splitting equals neighboring hydrogens plus 1. 2 plus 1 equals 3. We get a triplet. Apply that to bromoethane here. They're claiming that peak A is due to the CH2 here, and peak B is due to the CH3 here. This is just a TMS peak for just lining up your sample for calibrating, so please ignore that. And the CH2, the area of it should be a little smaller than that one. Now, they didn't integrate it, but it certainly does look like this one has a larger area than that one. The splitting of this, I'm seeing a quartet. That makes sense because it has 3 neighboring hydrogens. Add 1, you get your quartet. This is a triplet because it has 2 neighboring hydrogens. Add 1, you get your triplet. Let's take a look at this one. CH3, CH2, OH. See if you can identify each peak. That CH3 should integrate to 3, but they didn't bother integrating, so we're going to focus on the splitting. This one is it should give rise to just a triplet, so it's not that one because I'm seeing a quartet plus a broad peak there. So that CH3 is going to split into a triplet right there. So the green one is there. The CH2, we're seeing a quartet, makes sense. 3 neighboring hydrogens plus 1. That OH is not considered a neighbor because it's next to an oxygen, so it's considered its own separate beast. That being the case, it has no neighboring hydrogens and should show up as a 1H singlet, meaning in area is 1. There it is right there. It's a singlet. And these are notoriously unreliable because water can mess it up, things like that. But there's your 1H singlet there. And that is the NMR spectrum of ethanol. I recommend you only focus on first the area of the peak, which is easy. It's just the number of hydrogens. And then focus on the splitting, which is not that bad. It's neighboring hydrogens plus 1. Neither of these samples had neighboring hydrogens on both sides, but that's not uncommon. Simply add up the total plus 1, and you'll get the splitting pattern for those hydrogens. That's NMR spectroscopy, a brief introduction.